All right, we're going to go ahead and get started on chapter 4.2, Embracing Diversity of Algorithms. So, what we're going to introduce here are different ways to solve computational problems, addition, subtraction, right? Beyond what's we call the standard algorithm, right? Beyond what has kind of been adopted by elementary classrooms, which again, the algorithms are awesome and amazing, but we want students to have a pathway into them to understand that they come from somewhere, but then also that there are thinking strategies, right? There are different ways that we can approach solving them. So let's look at one of the first ones here, the dot method. Again, it can look a little confusing here a little bit, but let me show you by doing. And what you need here is single digit proficiency. So I've done 3 of them, but let's do one and then you can go back and look at the ones that are in the notes there. So here's a list of numbers, and here's how we would go approach this. I know this answer is 52 in the end, but let's go ahead and take a look at how we would solve it. And again, to be able to do a dot problem, the dot method, you need single digit proficiency, as we talked about before. But that's true in general all the time. Students need that. Without the single digit proficiency, um, they're going to struggle, right? So we want to make sure we are there for addition, subtraction, multiplication, and there are techniques to do that. 5 plus 8 is 13. So I put the 3 and put a dot to represent the 1. Okay. 3 plus 7 is 10. So I put a dot and then the 0. So we're doing single digit, and I'm just keeping track of the digits, the single digits. 0 plus 6 is 6. 6 plus 3 is 9. 9 plus 9 is 18. So I just put a dot for every one. 8 plus 2 is 10. So 0. 0 plus 5 is 5. 5 plus 7 is 12. Carry the 2 or put the dot there. And then once we have that, we just count the dots. The dots are tens: 10, 20, 30, 40, 50. So the answer is 52. It's that easy. And you're like, wow, I hadn't seen it. Yeah, that's that easy. There are different techniques to use. So you can go ahead and take a look at some that are already done. 2 plus 9 is 11. Dot 1. 1 plus 8. However language you want to use, up to you. But that's kind of a cool trick there. Or trick, not a trick. It's just a different way to organize your thinking. So what's beautiful about this method, that we could also do it horizontal format if you want. And we don't need a long list of numbers too, but we can go ahead and do that the same way. And so the middle one's not done yet, but we can take a look. It's been dotted already. 4 plus 9 is 13, right? So there's a dot, and then I put the 3. 3 plus 6 is 9. 9 plus 2 is 11. So there's the dot. 1 plus 9 is 10, dot. 0 plus 7 is 7. 7 plus 7 is 14, dot. 4 plus 6 is 10, dot. 0 plus 8 is 8. 8 plus 4 is 12, dot. 2 plus 8 is 10, dot. So I know the last digit's 0, and then you just count them up. 10, 20, 30, 40, 50, 60, 70. This equals 70. That's it. That's how it goes. Go ahead and try that again. It's not going to be your standard algorithm. It is a alternative algorithm. What's the standard algorithm? The standard algorithm is what you already know and learned, right? It's the common strategy that we teach in elementary school. It's the left to right standard algorithm. You can see this example's done. Just put it on top of each other. This will be always your first instinct to go to, because that's what you learned. 28 plus 45, 13, carry the 1, 1 plus 2. And it's efficient, so it works. Remember, compare this and contrast to the thinking strategies we've learned. And just to remind you, right, a thinking strategy would have been, in my mind, 20 plus 40, 8 plus 5, so it's 60 plus 13, 73, right? That's the thinking strategy. You're going to say that's too much. Yeah, but yeah, I did it in my head. But again, this is thinking. The other one's just kind of our single digit arithmetic and then remembering the process. If you want to look inside of our what you would do in an elementary school class, you would use base 10 blocks that look like this. And then you could do those problems, right? There's 20 plus or there's, sorry, that's 210, right? You could use base blocks. And so I have that link in the textbook here if you need it to kind of play with it. But that's where um, our standard algorithm comes from. You build it from the base blocks. And if we were in class, we'd play with it a little bit so that you could learn where that comes from, right? When we have too many, we regroup by tens, right? So something to think about. Remember how you learn base 5 arithmetic to keep that in mind. Another strategy is by adding with expanded notation. That's another strategy you could use. So 43 plus 47 would be 40 plus 40, right? You add by each of the place values, right? We call the partial sums method after 40 plus 40, 3 plus 7, right? And then you can add those partial sums. We're doing in between sums. What's better? Whatever the student can think of, right? And so you see partial sums there as we do that. Here's a longer kind of explanation here, but these are partial sums, and this works too. This is actually a good way to think about it when we get to algebra. We have variables, and we have to do some algebra. So something to think about. We'll end this little section on the partial wonder plate grow real quick, but you could see sometimes we call this the intermediate algorithm or partial sums algorithm, where we actually intentionally do it. So think about, I'm going to do the standard algorithm real quick down here, and then you can compare and contrast. 859 plus 467. So the standard algorithm is just to add the pieces from right to left. This would be 16. And so because I have 16, 9 plus 7, 16, I have another group of 10. So I give the 10 over here because this turned into 16, right? So I'm going to, that's another group of 10. And remember, base 10, we group things by groups of 10. So now I have 10 plus 5, which was 10 plus 50 technically, but we just keep track of the 1, 6, and that's 12. 6 plus 6 is 12. So I have 12 tens, which is 120 technically. So I have 12 tens, and then I give the 100 to the hundreds column. And now I have 13, and there's your 1300. But we get the same answer, but something to think about. This is more of a thinking strategy here, this partial sums, and then this is kind of, once I know my single digit algorithm, we give them an efficient way to do it in less steps technically. But let's see. Less steps. I can mentally do this. I don't have to write that down technically, but up to you, like what's faster. And then you have this one over here, another example to show you there, which is, again, the same way, but starting from left to right, actually. So either way works. See how it doesn't matter? Like, oh, I never thought about that. I can go left to right. You don't have to go right to left. You can go left to right too. But remember, we use algorithms to kind of standardize the process for everyone.